Yes. So, Mr. Subhan, do you have the Professor Patil's presentation, or Professor Patil has to
I
present
have to
it
share. I have to
repeatedly?
share my screen, but
Yeah,
okay, now I can do
yeah,
that.
I
Okay,
think, yeah,
that's good.
I
That's good.
think it's better you do it by yourself.
Yeah. That's fine. Can you see the? Can you see this slide here? My slide?
Yes.
Okay, just a
It's
minute.
already there. The presentation already there.
Okay, so all right. So very good morning for you from India. So let me begin by thanking Professor Katini and the organizers for giving me this opportunity to share some of our recent activities in the area of energy storage. So today I will be talking about chemistry for a redox flow battery. The main focus of the talk will be on a redox flow battery. So before I go to the technical aspect of my presentations, let me briefly show where I'm coming from. So I'm currently a faculty member in this premier research institute of India called Indian Institute of Science in Bangalore. We are located in the southern part of the India. This institute is established in 1909. So we are more than a century old. And this institute was established by this industrialist and entrepreneur, Jamshedji Tata. This was conceived in 1892, soon after the establishment of research universities in US and in Johns Hopkins and Caltech. So the land was generously donated by Maharaja of Mysore. Maharaja was, rather his mother donated. You see the Maharaja when the land was donated was a small child. So, and this, the mandate for the institute is higher education and research in science and engineering. And the earlier department were established in 1911 with chemistry and electro technology. And currently we have around 450 faculty and 4,000 students. So this is a lush green, beautiful campus. It is not yet concretized. And you can see the institute is located right in the city here. So, so this is a little bit about what we do at IISc Bangalore. My research group is a group of chemists, and we are synthetic chemists. We are, involved in design and synthesis of molecular semiconductors. So our main focus is we would like to invent new materials for a range of applications. So this is a little bit a very broad aspect of energy storage and generation. So we are currently involved in developing a new conjugated systems for organic solar cells. And the main focus is looking at some of the applications like agrivoltaics, building integrated photovoltaics, and indoor PV applications. We also use similar pi conjugated systems for a flow battery, which will be the main focus of my talk, and mainly for redox flow battery due to various aspects, which I will highlight very soon in my presentation. Due to a structural diversity and the potential for the redox flow battery is humongous. So we are currently involved in making materials for flow battery as well. So this is a rather a curiosity and a very exciting fundamental concept where how one can exceed the Shockley-Queisser limit, a thermodynamic limit for the solar cell applications. So we do molecular engineering for, to realize the concept, like take single photon and multiply into 2 so that we can boost the total efficiency of the solar cells. So we have other interests like near mid-IR photodetectors, organic LEDs and displays by using a similar concept in materials. So currently we are heavily involved in printing organic solar cells. So the idea is, can we really have a commercial viable technology based on molecular semiconductors, which involves, again, this is an interdisciplinary area of research. So we have to involve a synergy between a synthetic chemist, spectroscopist, and then we also work very closely with the theoreticians to optimize a molecular semiconductor for specific applications. So this is the main motivation of my talk. So as discussed by previous speakers, the world faces this terawatt challenge. And the most of the energy comes from by burning fossil fuels, coals, and other resources. You can see this is the collage map of a world, and the mainly lighting is a major sort of consumption of energy. You see the world is very bright, but essentially some part of the world is still under dark. If you in India looks very bright, but there are, I know, currently close to 40 million people up in India do not have access to the basic energy, light energy. So the demand is going to increase day by day, and the modern chemistry faces challenges. How are we going to generate energy, and how are we going to store the energy? Especially the regeneration, the regenerating sources such as wind and solar, they do fluctuate in the form of source of energy across the globe. Then you have to have a robust energy storage system. So that puts a lot of challenging demand on electrochemical energy storage devices. How are we going to store the energy generated by renewable sources? So that's a big challenge, and the challenge is the number looks to be very humongous. So this is the terawatt challenge. It's a main motivation for people across the globe, intensively looking for a robust energy generation as well as energy storage systems. So let me go back to the topic today, which I promised you. So redox flow battery is a very promising emerging energy storage technology. It's an electrochemical device. It works on the principle of a redox chemistry, where the beauty of the redox flow battery is the redox active species such as catholyte and anolyte are stored in a separate compartment. So this way you can decouple power and energy. What you do is you flow these anolyte and catholyte in electrochemical systems, and you do a chemistry at this interface. So here the anolyte undergoes reduction during charge, and the catholyte undergo oxidation, and you can keep flowing these anolyte and catholyte continuously and generate the power. So if you really want to increase the energy density of the battery, you can increase the concentration, or you can increase the tank size. And if you want to increase the power, you can increase either electrode surface area or the stack of the electrode. So this way, these two aspects, unlike in other batteries, are completely decoupled. So you have a flexibility where you can play with the power and energy independently. Of course, it's a very safe battery system. Unlike lithium battery, you must have heard there are a lot of issues with the lithium batteries. It can be operated at room temperature, and there are instances where it can be operated even at low temperature. So you can also do a deep discharge, unlike in a lead and lithium batteries, where you cannot really go for a very deep discharge. In case of a flow battery, you can also do a deep discharge. So in terms of applications, you can see these are what I have shown here is system power ratings versus discharge time at rated power. There are various battery technologies that have been listed on this plot, and flow battery is superior compared to all other batteries which have been shown here. Indeed, flow battery in terms of a rated power and a module size is way above than other batteries which are currently people are using. So it's a excellent technology per se for the grid storage applications. So, and then for the other aspects such as emergency backup, transmission, and distribution. So considering these aspects, we are indeed interested to develop a materials for redox flow battery. So redox flow battery can be very different types of redox flow batteries. There are all major types of redox flow battery. Currently, vanadium flow battery has been commercialized. So this is all liquid phase here. So both the catholyte and anolyte, which was shown in the previous slide in a separate tank, can be stored in the form of a liquid. It's a reservoir to flow through the electrochemical system. There are also hybrid batteries where one of the aspect is solid and another is liquid, such as zinc flow battery. And also there are other flow battery where both the aspects are in a solid phase. So I will not get into much into detail, but there are different types of redox flow battery which are emerging for the grid storage applications. So here is this is the slide essentially talks about advantage and disadvantage. So there are two types of redox flow battery, aqueous and non-aqueous. So aqueous flow battery is very cost effective. It is, but it's very limited due to a sort of a electrochemical potential with the water. So you see that when you use aqueous electrolyte, you have to really ensure that these processes doesn't take off. For example, oxygen evolution and hydrogen evolution. So you have to work in a very limited potential window when you use a aqueous electrolyte. So the potential becomes extremely narrow, and it has a limited temperature range. It can work in the range of 0 to 100 degree. And the redox couples are also very limited. You have to ensure that the redox couples are indeed soluble in aqueous system. So but considering the beauty of a safety, considering the cost of the electrolyte, this has been indeed demonstrated at pilot scale. And it is also, again, safety is a major advantage with the aqueous flow battery, because it's a non-flammable aqueous solutions electrolyte you use for flowing the battery. And so that's the reason this is indeed been actually demonstrated at pilot scale. Here comes the organic aspect. So where you use a non-aqueous electrolyte, you use the solvents which are electrochemically stable, but you can go with a very a large voltage window. You can go up to 5 volt in a non-aqueous electrolyte, and there is a structural diversity. You can play with the potential here with by changing the chemical potential at the redox couples. You can go up to 5 volt, up to -2 to 2. Play with the clever chemist always can tune the redox potential by introducing a various functional groups on these organic chromophores. And you can also play with this redox couple by introducing some inorganic organic complex systems such as ferrocene and other aspects. So this has with the advantage is mainly in terms of potential. It is also, you can dissolve, you can increase the solubility. This is the way you can really increase the energy density by using very high concentration electrolyte. And it has a sort of as I mentioned, it's a greater diversity. So in terms of, when I say greater diversity, you can tune the potential window from -2 to 2 volt here. Cost effectiveness, it's still a question of a debate. Certainly people are indeed looking for it. It's a very cost effective technology, can be done by using a very simple organic chromophore, and you have a large number of redox couple available compared to the aqueous. So if you see here, it's a very limited redox couples are available for aqueous electrolyte. And if you compare with the organics are indeed a very large window, and there is a greater diversity. So we are indeed interested in perhaps in both. So today I will show you how we approach this problem to looking at both aqueous and non-aqueous electrolyte. When you go for a non-aqueous electrolyte, so there are major challenges here. One of the major challenges is stability of these catholytes and anolytes. So you have to really work in a very narrow electrochemical potential window. There are two reactions which kicks off when you use these catholytes and anolytes as a redox couple. So you have to ensure that when you choose the redox couple, you have to ensure the energy or the LUMO level, the lowest unoccupied molecular orbitals of a anolyte has to be below 3.5, whereas a HOMO has to be highest occupied molecular orbital has to be in the above in this range. So if your energy levels positions outside this window, essentially what happens is this reaction kicks off. Soon after we do redox reactions, the electron, the reduced species can react with water and generate hydrogen. So this is a sort of unwanted reactions which you want to avoid. Similarly, when you do oxidation, the oxygen reacts here. When you, for example, the reduced species again can react with oxygen. and generate this hydroxy radical. So this way, what happens is this is a very narrow potential window. This is a sort of a guideline for designing a new molecules when you want to use any new molecules for the redox chemistry. So this is what one of the major challenge. You have very limited potential window in order to design rationally a new molecules for the redox flow battery. So this is true also for other applications in the area of photovoltaics or other applications also. So we, considering these aspects, we design initially a range of new molecules. This is something called diketopyrrole based systems. So our systems are indeed thought about it rationally. What if you look at my cursor here, what I'm showing here, you can see that we have a thiophene is a donor and a lactam, fused lactam, sorry, my apologies. So fused lactam is an acceptor, and you can really play with the solubility by introducing various alkyl chains here. So you can increase the concentration, and then I know this is a donor acceptor system. So you are electronically coupling a donor and acceptor and playing with HOMO and LUMO here. So essentially we can change a range of, by keeping the acceptor similar with the fused lactam, you can play with the donor group. For example, you can go with the pyridine, and then perhaps you can also introduce other nitrile functionality. So you can play with a functional group and tune the redox potential in an appropriate window to achieve the stability. So that's basically the idea here. So what essentially we did is we used this thiophene and selenophene as the heterostructures, and we used this nitrile functional groups. And this is the simple chemical reaction as I indicated in my previous slide. Simplicity is essential. So you have to really scale up these reactions in a gram scales. So you have to really do structural modifications cleverly and gain the stability. So this is what we did. We used this thiophene diketopyrrole material, which has a LUMO of 3.1 EV. And if you remember that 3.1 EV LUMO is not a stable analyte. Whereas when you do a structural modification, so you introduce the nitrile group here, then your LUMO goes much deeper. So you push the LUMO much deeper, and you get a LUMO level now -4 EV. So essentially now you can use this material as a good analyte because it has a very high electron affinity, it has a very deep LUMO, and it's an air stable material. The reactions which I showed in the previous slide are, this is something which is more inert to those reactions. What, I was talking about reactions with water and oxygen. So let's look at the electrochemistry of these materials, what we developed in our lab. You see that very clearly. This is the thiophene diketopyrrole. You have it does get oxidized and reduced. It's a redox reaction, but the magnitude of the current is very low here. So I would say it's a reversible system, but perhaps considering the current densities here, so this we cannot really use a material for the flow battery if you want aiming for very long cycles. Whereas when you go for a selenophene nitrile and thiophene nitrile, we see a beautiful cyclic voltogram. And then you see that this is a 2-electron redox, beautifully reversible process here. And the magnitude of the current is also very high. So you can reduce multiple times this by using a different electrolyte, which I'll show in a minute. Is pyridine, we did not get, again, reversible series here. You see here, if you're looking at my cursor here, we can see that it does get reduced, but it is not really comes back again with the similar magnitude of the current. So we were indeed, when we screen out by just doing a simple experiment in the laboratory, by doing electrochemical experiment, we observed that this material, these two materials are a potential candidate for the redox flow battery. So then we, sort of built a battery. We took a analyte here. This is we use as an analyte based on our previous experiment, what I showed. And we use two different catholyte. One is unisol blue and another is this dimethoxybenzene with a tertiary butyl group to increase the solubility. So these are commonly used catholytes in a flow battery cell. And we were not the first one, but we were the first one to use this analyte in a flow battery. And this is the typical cell. So here we also optimize the electrolyte, which is the best electrolyte we can use for the, if you use this as an analyte. It's very important to find the right pair to identify a electrolyte as well as a supporting electrolyte for the flow battery. So there are different electrolytes we use. This is TBA-PF6, sodium triplet, and lithium TFSI. You see that in case of TBA-PF6, we see a much better redox cycles. These are large number of multiple cycles we could run, but sodium triplet turns out to be not that stable and a good supporting electrolyte for this system. And whereas lithium TFSI also turns out to be a very good electrolyte. So by using this screening of the electrolyte, we also optimize anolyte concentration, and a supporting electrolyte. So these are basically this idea of before we build the battery here. Now you can see that now we screen out again. Perhaps we subsequently do another electrochemical experiment, but what we do is essentially we take Unicell Blue and DBB here, and then with the same electrolyte, and identify the potential window here. Theoretically, how much voltages we are going to get when you build actually a flow battery by using these two electrolytes. We have a catholyte here, Unicell Blue in this case, and we have anolyte with which we synthesize in our lab. Similarly, the DBB is the catholyte here, and we have anolyte synthesized in our laboratory. So we first identify what is the maximum potential window we could go while charging and discharging the battery here. So this is our cell. Finally, we fabricate the battery. This is a typical cell, a laboratory made cell, where we have a sort of stainless steel plate. Okay, these are the stainless steel plate, and we have connectors, and we can put a Nafion as a membrane here. So when you use this non-aqueous flow battery, it's very important to use Nafion as a membrane, and we have electrolyte inlet and outlet for the flow battery. So these are inlet and outlet. It's a typical electrochemical cell. So this is first a galvanistic data, charge discharge data here for this, Unicell Blue, and the one which the material anolyte prepared in our laboratory. You can see that we can see a sort of two redox processes here actually when we do a galvanistic charge discharge. And interestingly, what happened is the charge, when you go for up to 100 cycle, you see there is a clear this is the sort of, when you go for multiple cycles, charge discharge cycles, you see the capacity is fading slowly. But what we could maintain a good Coulombic efficiency and voltage efficiency in this cells when you use the pair Unicell Blue as a catholyte and thiophene nitride as an anolyte. Then we also do similar thing with the DBB as a catholyte and thiophene DPP as a anolyte. And similarly, in this case also, we see the capacity fades away because of the, again, perhaps one of the system, either it's a catholyte or anolyte, is not stable. So this data clearly shows that there is something is wrong in our catholyte and anolyte system, but we could get a very good Coulombic efficiency. So to investigate further, to understand where things went wrong, we did this symmetric flow cell studies. So this is 50% SOC. This is a typical Michael Aziz in Harvard has introduced this to sort of understand to stability problem of these flow cells. So we use the similar procedure just to understand which is what went wrong in our cells. So, and then fabricate the symmetric flow cell. Then this is, you see that here is thiophene nitride with which we synthesize in our lab. We can go up to 700 cycles. No, the capacity remains same. So it does not really, what does it mean is essentially the anolyte which is synthesized in our laboratory is very robust and very stable anolyte. When you do similar studies with the Unicell Blue as a symmetric flow cell, we can clearly say it indeed decays over a period of time. So what we attribute is the catholyte which we are using, which are commercially available catholytes, is not stable, whereas the one which we made as an anolyte is indeed stable. So I started saying that you have to rationally design these catholites and anolytes. And when we push the glue more deep and deep and deep, essentially this turns out to be very stable anolyte. We went again further ahead and then did a very detailed spectroscopic characterization. What are the species which are not? This is a very busy slide. What we do is under two different conditions, under ambient conditions, under inert atmospheric conditions. When you do a battery inside the glow box and outside the glow box, when you do these reactions, you see that this unisol blue neutral has this typical characteristic peaks in a UV visible absorption. And then when we go for 5 hours to 1 day, you can see that there is indeed a change in a spectral signature of a unisol blue, and the peak do change the position as well. So that clearly indicates that this unisol blue degrades over a period of time. Similar with DBB. DBB has this typical UV visible absorption peaks in the range of 200 to 500 nanometer, but it's over a period of time when you discharge, you see that it's indeed discharge. Whereas when you go to thiophene nitrile, you see that thiophene nitrile is indeed very stable. You do not see any such degradation. But under ambient conditions, all these molecules have a stability problem. Under ambient conditions, this is indeed further degrades very fast. This also degrades, and you see also this unisol blue, it remains stable. The positions, the peak remains same, and you see this is the peak which I was referring to. After reducing, you see this typical signature, and that remains at the similar position. So what it does, what we can rationally conclude based on this experiment, indeed thiophene DPP hexyl CN4 is a very stable anolyte in ambient conditions as well as in a inert atmosphere. So this is first part. Actually, let me summarize. So what we did here is we identified a new class of anolyte based on the organic redox flow battery. We also did the proof of concept by demonstrating the cell. And what we identified is, the flow cells can be stable in an inert condition up to 100 cycles. Whereas the major take-home message is the symmetric flow cell studies is stable up to 700 cycles. So our rational design of an anolyte by using this donor acceptor concept indeed works, and we can now we indeed prove that this thiophene DPP based systems is a very good anolyte. So let me go for the aqueous part now. So this is non-aqueous battery, what I have shown in the first part of the talk. So let's move to the non-aqueous flow battery. So non-aqueous flow battery, we works on this soluble lead redox flow battery. So there are many advantage and disadvantage here, the battery kind of battery we are working on. So it's mainly we use a single reservoir here. So what we use is a lead methane sulfonate salt dissolved in methane sulfonic acid, and we circulate a single electrolyte solution. So you do not need a separator. So this is the major advantage in terms of the cost. So this is a very cost-effective flow battery. This has been already practiced in the literature. It has a single electrolyte, not two different taps. So it's a low-cost active material, and it's widely abundant. It's a similar like lead battery, whatever people have done it. So, but there are challenges again. There are many challenges when you are demonstrating this battery at scaling up the battery at a large scale. One of the major challenges is this dendrite growth. You can see this is anode. You see that lead converts into a dendrite formation. You have also other problem is oxygen evolution. And you see that this lead oxide sludge indeed forms here. You can see this picture here clearly in a frame here. This will the dendrite will fall back as this lead oxide sludge here. So to mitigate this problem, so we started working on this battery 4-5 years ago. It's one of our PhD student has completed PhD here, and this is the typical reaction takes place here. Of course, on the cathode side, lead is get oxidized to lead oxide, and anode side is it can get reduced to the lead metal. The overall cell voltages you can go up to 1.62. So this is sort of an overall cell reaction. So to mitigate this problem, there are challenges we identified first. And to mitigate this problem, we did some first use anode and cathode as various additives here. So these are the additives we identified to, first to address the question of how do we avoid the growth of the dendrite here. So we use anionic surfactant, cationic surfactant, and non-anionic surfactant. So first, what these additives do, these additives, can they prevent dendrite formation when you add any electrolyte? And can they really, in whatever the overpotential we are seeing at oxygen evolution at the cathode, and then they can increase the strong adhesion of the lead oxide. So let's see what essentially these additives did in our case. So this is the typical cell. Again, we made a small scale cell in our lab, and then we first do identify the role of these additives here. So basically we have again a cathode mounted a polycarbonate sheet. We use flexible graphite felt as a current collector, and we have and then we have a reference electrode holder, and these are the very detailed about this cell. So we first do a small scale studies. What is the role of these additives here? So for this purpose, we went ahead and did first study here. You see that at the anode, okay, you can see that these lead dendrite, huge growth of a dendrite, the surface becomes very, very porous after adding sodium fluoride. And Triton X100 and sodium fluoride binary additive systems, by adding that solution, it results into a very uniform and porous deposition. And surprisingly, when we add HDTMA and sodium fluoride as a binary additive systems, you see that it's a very smooth deposition of a lead along a lateral direction. So it works. It works beautifully. When you use these additives, it clearly indicates that we could avoid the growth of this, the lead and the dendrites on a electrode. So learning this lesson, we went ahead and then did a charge-discharge cycle. Here you can see that pristine electrolyte, you see there is a Coulombic efficiency. When you do a charge-discharge cycle, you see there's a fluctuation. There is a lot of noisy sort of a, you do see these spikes, and also efficiency drops. So that clearly shows that it is pristine electrolyte has this dendrite growth problem. Whereas when you add a SLS and sodium fluoride, you do see such fluctuation, but it is the Coulombic efficiency is much, much better. But then we have different binary additives, SLS, sodium fluoride, HDMS. Surprisingly, when you add HDTMS and sodium fluoride, we see a very stable Coulombic efficiency. So there is no any such spikes, and it was stable up to 1500. So we first, by doing this experiment, what we did is essentially we identified this is the good electrolyte additives for, and this is a very good optimized additives for adding into the electrolyte. So going forward, we did a sort of a engineering, and then we started scaling up. Okay. And we first we addressed the question of this dendrite growth. Then there is something called a shunt current in a flow battery, which is very common. It's a leakage current, which essentially, again, is sort of, highly undesirable and then it also causes this non-uniform voltage fluctuation distribution, across the stack when you put multiple stacks. So essentially, this need to be avoid when you are operating battery at large number of charge discharge cycles. So to do this, we have mitigated the shunt current problem also by using sort of a different method here. There are different experimental methods in the literature people use. We use a very simple multimeter method where we measure the current at the exit and entry point. So this is by using some sort of, and then we use this equivalent circuit model. And there are other methods which I mentioned. You see that magnetic field detectors, voltage draw along, electrolyte in channel and manifold. Those are there is a complexity involved in those experimental methods. Whereas in our case, we simply use this equivalent circuit model and try to, see, identify where are the very origin of a leakage current. in a such as a large stack here. So with this method, first of all, we use different manifold to flow the liquids. We use external manifold as well as internal manifold. But the idea of using these manifold is what happens to the shunt current when so if you see that when we use the external manifold, for example, and internal manifold, how we can address the question of a shunt current. So this is a simple objective of these experiment. So we, to find out total stack voltage, electrolyte conductivity, and then a design of electrolyte. So essentially the shunt current depends upon a variety of factors. It's not only the resistance built across the stack, but it also depend upon total stack, the electrolyte conductivity. And the conductivity of the electrolyte is very, very important here, because we are also adding additives to address the question of this dendrite growth. So remember that when you add these additives, the question is what happens to the conductivity of the electrolyte. And when you put these manifolds externally and internally, they have their own resistance built by adding these manifolds externally as well as internally. So we just wanted to identify if you increase the path length by very long channels by putting these manifolds outside like this, then you have a additional resistance built in a battery. So we wanted to see what the role of each parameter and mitigate the question of a shunt resistance. So we went ahead and made 3-cell stack, 5-cell stack, 7 cells, and 8 cell. So you see that. So this is initially, these are all LEDs are glowing by the battery. So first, we did a very simple experiment with the 3-cell stack to identify the shunt current, and we went up to 5 cells, 7 cell, and then we started sort of scaling up the battery here. We went up to 13.5 volt in 8-cell stack, and you see that these are all external manifolds which I was talking about. Our tank is here. We flow a liquid with the external manifold inside this stack here, and this is our outlet. By doing this one, we wanted to sort of identify whether you want to put manifold inside or outside like this, external manifold or an internal manifold. So idea of going from here to here is, when you increase, what we are doing is essentially we are also increasing the surface area of the electrode. So we are increasing surface area of the electrode, we are increasing the size of the tank, and we are also flowing the liquid by using external manifold. So these parameters indeed adds to the shunt current. So this is our first internal current distribution. You see that with the different charge and discharge. With internal manifold design, when we have manifolds are inside, what we see that there is indeed a charge current found to be decreased from 3, 5 to 7 cells. With external manifold design, there is a deviation in the applied current, but what we identified, there is an ionic leakage current when you use external manifold. So this is a very important results when we are scaling up the battery. It's very important to understand these fundamental aspects of the battery. When we have what happens when you have external manifold, and what happens we have internal manifold, and how that essentially causes the leakage current within the stack. So this is the important lesson we learned by doing the external and internal manifold. And you can see that now what happens with the internal manifold. With internal manifold, when you do charge discharge, what we learn is the middle cell, which polarizes much faster than the terminal cell. So this is again due to shunt current. So when you use this internal manifold, and you can go for a large number of charge discharge with a different flow rate here. These are all different, flow rate. And you see that
Professor Patil, 2 more
how
minutes.
Much?
2 more
One
minutes.
More.
2 more minutes.
Okay, that's fine. Okay, that's good. So I'm almost done there. Sorry. So this is what the lesson we learned. And then finally, what we do is we run these batteries for very large number of cycles. So by using this 8-stack cell, and we try to identify the efficiency and cycle number. So this is a very comprehensive data we have collected in our lab. And finally, now I'm coming to the end. What we demonstrate here is a 8-cell stack redox flow battery. Okay, well, this is what we designed. And we also identified the problems, how to mitigate dendrite growths, how to design the manifold, whether the external manifold, what it turns out to be that external manifold has a adverse effect on the shunt current. So we have demonstrated battery at 12 volt 250 watt hour, and now we are taking up to 1 kilowatt. So in our lab, this is ongoing work, so we are doing it now up to 1 kilowatt. The stack showed here stable cycles, and this is what the currently ongoing test in the laboratory. So so this is our work. We started sometime in 2016. These are all basic studies were done in this single cell, 24 centimeter square area. Now we are here in 2021. At the end, we have 8-cell stack. So we demonstrate a full functional prototype battery by doing, but it is very, very important to understand the fundamental aspects of the battery at small cell stack, and before we demonstrate such a prototype. So this is the students which are, perhaps I can play this video. You can see that how we assemble this 8-cell stack batteries, flow battery in the lab. So let me just, in interest of time, let me play faster so you can see that these are all the see our 8-cell stack looks like this in the lab currently, what we demonstrate, and then we can put entirely a 8-cell stack battery in this fashion. So with this, let me thank you, my collaborators. We work very closely with our senior faculty colleague in the same department, Professor Ashok Shukla, and there's a younger colleague, Professor Nagafani Atikuri. And this is the PhD student who worked on this entire thesis on a non-aqueous flow battery, whereas a non-aqueous flow battery work by Shikha Sharma, and aqueous flow battery Suman Rathod, and now a new PhD students took over the project from this one. These are we are grateful to these funding agencies for funding this research. With this, I will be happy to answer questions, and thank you very much for your kind invitation for this meeting. Thank you very much.